Newton's father was an affluent farmer that died just before Isaac was born. When he was born, he was a premature baby, and very small. Obviously he survived, and his mom remarried shortly afterwards to a clergyman that Newton hated all his life. Newton never studied mathematics in school. That came in the university once he went to Cambridge. At Cambridge, they taught Aristotelian studies and ancient Greek mathematics, the Greek of Euclid, which you guys learned also in elementary school, middle school, maybe even high school. So he taught himself the works of Copernicus, Kepler, Galileo, and Descartes. He then proceeded to invent physics used by civil and mechanical engineers until the present time, calculus, that was co-invented with Leibniz, optics, the marriage of physics and astronomy called still astrophysics. He himself, by the way, was never married. Not to be too bored with his life, I guess, he became the head of the Royal Astronomical Society and proceeded to use that role to make the life of people like Leibniz and scientist Robert Hooke hell. Also, he was the head of the Royal Mint. That means he was responsible for minting coins. In that role, he also became a detective. He would go undercover into pubs and actually catch forgers that way. He helped convict, hang, and quarter forgers that he discovered. On top of that, he was a prolific theologian that rejected the worship of Jesus as God, but strongly believed in a benevolent Christian God. He also spent half his time on alchemy, the field of study that at the time was involved in trying to turn lead into gold. But we have limited information on that part of his life. When he finished his undergraduate degree, Newton had to go home because of the plague. That was in 1665. Over the next 2 years he was at home, in his father's home, where he proceeded to invent the basics of gravitational theory, calculus, and optics. We will spend a little bit of time in this lecture about gravitational theory. Story goes that Newton has seen an apple fall from a tree and thought, hey, this apple is being attracted towards the center of the earth. A more reasonable story also says that there was wind and the apple was falling sideways and moving in a shape that was fairly parabolic. Galileo Galilei, if you recall, was actually using his understanding of gravity to explain the parabolic orbits of cannonballs. That was a clue. Newton thought to himself, why shouldn't gravity that affects the ball here on Earth, or that affects the apple here on Earth, extend all the way to the moon? He took the results from Galileo and extended them to the moon with the following idea. How about if some form of gravity was also affecting the Earth from the Sun? Now we know what happens between the Earth and the Sun. Kepler's third law works there. What if a modified Kepler law worked between the Earth and the Moon? Here we go. We have an apple that could fall onto the Earth, or if I throw it hard enough, doesn't only work in a parabola, but actually is affected by the Earth so that eventually it comes back and hit you in the back of the head. He calculated that and found out that it's about an hour and a half for the apple to go all around the Earth. Remember, by that time they knew the Earth's circumference, and he knew the acceleration due to gravity at Earth's surface. He then proceeded to ask the following question. How strong would gravity have to be at the moon's distance? Well, using this modified Kepler law, he calculated that gravity. It was not the same as gravity on the surface of Earth. It had to be a little smaller. And figured out how long the moon would take to go around the Earth. Remember that Kepler's third law relates the distance to the period. Using that relationship, Newton invented the universal law of gravitation. Let's test Newton's idea about gravity and the moon a little closer. If you have a great pitcher that throws a ball horizontally, that ball would fly once it leaves the pitcher's hand in one line in one direction, unless gravity does something to it. Well, obviously it does. Eventually the ball would move in a shape that's parabolic and fall to the ground. But if the Kansas City Royals are very lucky, they land the pitcher from hell, and he's throwing a ball that is so fast that it curves exactly with the curvature of Earth, thus coming back in a circular orbit and coming all the way back to Earth, coming all the way back to the original position after 90 minutes. That's the initial throw. Well, if there is gravity acting on the moon and the pitcher from hell threw the moon at some sort of speed to begin with, not towards the Earth, but in a direction that's perpendicular to the direction of towards Earth, then the moon would move around the Earth in a circular orbit. We've already figured out, and Newton knew, what the circumference of the orbit of the moon was. We also knew that that circumference is traversed in about a month, in about just under 30 days. Take those two and make a ratio and you have a velocity. That velocity can be used to find the acceleration and therefore also basically how much gravity there is at that particular distance. That's for circular motion. Let's go back to that pitcher from hell, but this time around let's have him still on Earth and hurling his baseball at a speed that is a little bit faster than the one that got the ball to move in circular orbit around Earth. What then? In that case, the ball, still affected very much by gravity, changes its direction quite dramatically, but there is enough of a speed for it to escape a little further from Earth's origin. Therefore, as a result, as it moves further and further out, it moves slower and slower. And therefore, it sweeps equal areas in equal times as Kepler's second law would have it. That's why it would move in an orbit that resembles an ellipse. And we have completed completely explain the three laws of Kepler without any harmonies of the world. What we just described are the three laws of Newton, only we never use those words. Newton's first law is actually the same idea by Avicenna, the Muslim scholar from the 11th century, and by Galileo Galilei, which is that objects move in one direction along a straight line in one speed if you don't force them to do anything else. If you threw a baseball in empty space, no gravity. It doesn't matter that you threw it. It would keep on going and going and going and going. Nothing would stop it. That's very different than Aristotle's idea that was in order to keep things moving, you had to keep on forcing them to move. Of course, the reason for Aristotle's confusion was that on Earth we get a lot of friction and drag and air resistance and things of that nature. The second law was also to a certain extent described by Galileo. Objects that were acted upon, for example by gravity, were speeding up. What Newton added is that you can use geometry especially to show that this speeding up and slowing down can be augmented by change of direction. That was the main reason for his invention of calculus. The third law, that for every force in action there is a reaction, is something that's very obvious if you, for example, push on the wall right next to you. You push on the wall and you can feel the push backwards by the wall on you. Earth's acting on you. Earth is pulling on you. As a result, you pull on the Earth. Now you were saying, what? I'm pulling on Earth? Of course you are. But you're not gonna speed it up by much. You're gonna be fairly negligible. We would have to have all masses acting on it together in order that you can figure out that there's lots of masses that can pull on lots of masses. That's the other reason Newton invented calculus. The universal law of gravitation is described in the next two lines and also in the formula on the next page. This is one of the very few equations that I will include in this whole class. Another one that will come much later would be E equals mc squared. But don't expect more than one or two other equations throughout. This equation is called the universal law of gravitation by Isaac Newton. What it says is the following. The force between two objects is proportional to mass 1, uppercase m, times mass 2, lowercase m, times some number divided by the distance between them squared. That's exactly the same as we had in the previous slide. Now this is a relationship that held true until the last 100 years. 100 years ago, Albert Einstein figured out that this equation should be modified. But from the 1600s and until 1915, this universal gravitation law held supreme. This is the equation that is implicit in all of the laws of the previous slide. Newton's first triumph was his prediction that there should be 2 tides in every day. Galileo Galilei predicted 1 tide a day, and that agreed with the very weird shape of the Mediterranean. Over the rest of planet Earth, tides appear twice every day, and we will learn about that next in the next lecture. Another thing that Newton discovered is that the precession of the equinoxes can also be a result of gravitation. Both of those effects are the results of the moon back reaction on Earth. Also in Newton's day, Halley's comet appeared. Halley was a friend of Newton. Yes, he did have some friends. And Halley predicted that according to Newton's laws, that comet will come back in 76 years. It has been coming back every 76 years since, and was last near Earth in 1986. We call it a one-in-a-lifetime event that you can see that comet. Another effect is the fact that Earth has a beer belly. Since Earth is spinning, the water and the rest of the material of Earth is gonna be having an effect, kind of a centrifuge effect. That effect is gonna make Earth's middle a little bit thicker, and it's a little thicker to the tune of about 20 kilometers or about 12 miles, which means that Earth's oblateness is even larger than Mount Everest. Therefore, the point that's furthest from the center of the Earth on Earth is not Mount Everest at all, but rather a volcano in Ecuador. Earth's gravity makes the moon move in a circular orbit around the Earth. The moon, in return, acts backwards on Earth and its oceans. In this picture we see Earth from above and a thin skin of ocean. You would note that the ocean is nowhere much more than a few miles in thickness, whereas the Earth's radius is about 4,000 miles. Therefore it's not a huge thick skin like you're seeing right here. It's way thinner than that. Still, there is an effect, and that effect is very much noticeable. That effect is the effect of the tides that we will see in the next picture. The simplest way of explaining tides is looking at the pull by the moon on parts of the Earth. The part closest to the moon is the ocean skin right next to that moon. Then it pulls a little less on matter in the middle of the Earth and a little less still on the other side of the Earth. Of course, the arrows in the picture below are ridiculously exaggerated. They're almost equal in length with slight differences, but it is so that the largest arrow is nearest the moon and the furthest is the smallest. That's how Earth now has a slightly deeper ocean in the direction of the moon, hence high tide, and slightly deeper ocean on the opposite direction of the moon, hence high tide there as well. Now take into consideration the fact that Earth spins on its axis once in roughly 24 hours. That means that if there is a person standing on the side of the moon in the ocean, that ocean is about 3 feet deeper than if that person stands at 90 degrees to the moon. If, for example, this is a full moon, that means that at midnight the tide is the highest, and at sunrise and sunset the tide is lowest, and at midday the tide is the deepest. Tide tables helped the English rule the world because they knew when to get their merchant ships and their warships into and out of harbors fairly accurately. And of course Newton provided with a more detailed tide tables for both North America and England, therefore helping out the British Navy find a place where to dock. Even the sun has an effect on the tide. When the moon and sun together act, you get deeper tide. Basically, the sun does have a way bigger force on the earth, but the difference between the force on the side of the sun and the force on the side away from the sun is smaller than the difference between the pull by the moon on one side and the pull by the moon on the other side. Thus, it's the moon that's responsible for the major tides. Yet, when both of them work together, you get deeper tides. Therefore, if you want your aircraft carrier to get out of the harbor, the best time would be not only when it's the moon that's closest to overhead, but also when the moon and the sun are lined up, meaning either full or new moon. These are called spring tides, whereas when the tide works against that tide by the sun, that's called neap tide, and the average on Earth is 2 feet difference, whereas it's 4 feet when it's spring tides. There are places on Earth, seen in the next slide, where the tide ends up being way different, way larger in difference. But these are very spatial peninsulas and bays where this tide is very much different. In most places on Earth, it's a 3 feet on average difference, 4 feet in spring tide, 2 feet in neap tides. The difference between tides in Mount Saint Michel and the Bay of Fundy are among the biggest on Earth. There the differences can become all the way to 30 feet difference rather than 3 feet. Another effect that is due to the moon, especially due to the moon, is the change in Earth's axis of rotation. Yes, there is a change. So far, I've neglected that. I said that Earth's axis of rotation is always tilted so that it's towards the sun in our summer and away from the sun in our winter, and the north is only under Polaris, the pole star. That's technically correct on a time scale of years. On the time scale of tens of thousands of years, however, that is incorrect. In the next slide I will discuss why that is incorrect. Of course, that's tied up with gravity. Now we're going to see how the effect of gyroscopy works on Earth. You may know the effect of gyroscopy if you ever rode bike or motorcycle. When you ride your bike and lean sideways, what the bike actually does is veer in that direction rather than fall. And you veer despite the fact that you do not swivel the front wheel at all. This is similar to what happens to a gyroscope. I have a picture here of a top or a dreidel that's spinning. That's an example of a gyroscope. As it actually goes sideways a little bit, it does this motion called precession. On the left you see a force by the moon on Earth's bulge. Earth's tilted by 23.5 degrees. The moon is trying to straighten it up. Rather than the bike trying to be put down, here the moon is trying to straighten the Earth up. How? By acting on the bulge in a way that tries to straighten it up. The effect is not huge. What it does to Earth's axis is it makes it swivel like a top. It makes it precess like a top. Look at the effect in the next slide. Now let's see what that effect does to our North Star. As we stated fairly early on, if you look north at about your latitude above the horizon, you will see Polaris, the North Star. If you were on Earth's North Star, Polaris will be right above your head. In this picture, you see how to find Polaris, the North Star, by looking at the Big Dipper and some constellations in that direction. Now, what would that swiveling motion do to the North Star? More on that in the next slide. The consequences of Earth's axis of rotation precession is that the North Star today is not going to be the same as it is in a few thousand years. About 5,000 years ago, the ancient Egyptians recorded the star Thuban as the pole star, or their Polaris, their North Star. In 13,000 years, the pole star will be very nearly Vega. In 26,000 years, Polaris would be exactly our pole star again. So, from season to season, from year to year, in a human lifetime, Polaris is still going to be our North Star. But in a matter of thousands of years, the North Star does precession in the heavens. Look at this picture below. This is a picture of where the vernal equinox, that is, where the sun is, in what constellation in the sky. If, of course, the day sky was dark, we would see the sun not exactly in the March constellation of Pisces, but actually a little bit towards the February constellation of Aquarius. You may recall that the sun rises with Taurus the Bull in May, with Gemini in June, etc. Now that was exactly true 2,000 years ago, when horoscope became big, when the religion of astrology became really big. That's when it began. It is no longer true now. The vernal equinox was in the middle of Pisces, and now it is going towards Aquarius. In 13,000 years, the vernal equinox will be in Virgo. The constellation of Taurus will rise with the sun in November. That is the other reason that's the other result of the precession of Earth's axis of rotation. This is called the precession of the equinoxes, and was actually known to Hipparchus, an astronomer, at 200 BC. Something that was not as well known is the effect of the moon and the sun working together, or not exactly together, on that precession. Now remember, there are two effects here. One is that sometimes the sun and the moon work together on trying to straighten up the Earth, and sometimes not exactly together, therefore not as effectively. And the other is that sometimes the sun is the closest to the Earth, because Earth is closest to the sun in its ellipse, and the moon is closest to the Earth in its ellipse, and that's when you get the most effect. And if it's not exactly in that peak, then you get the least effect. Both of those together make that precession not exactly circular in the sky, and more on that in the next slide. That picture in the sky that was supposed to be a circle has slight nutation or slight waltzing motion as you go around in the circles. So basically this is that motion of the pole star as a function of time. Those little loops are greatly exaggerated here. It's very nearly a circle. Those little changes are in matter of arc seconds, whereas the actual tilt of Earth, meaning the whole radius of this circle, is 23.5 degrees. When you look at each and every little waltz, there's also little waltzing in the waltzing, and that's the result of that elliptical motion I was discussing before. And you can see that that has a little bit of an effect as well. So if an astronomer looks and finds what the true north really is, and looks over many years, they would see both this precession of the pole star and the nutation of the pole star. This is the end of the effects that already were discussed by Newton in his great book Principia, that described the physics, how it works for celestial objects, and therefore the invention of astrophysics.